Hey there, welcome back to Short Takes 331. Today we continue on our path toward Quantum Monte Carlo. This is going to be our last episode in this sub-series of our Short Takes 331 series. And in this episode, we're going to talk about how to generate field configurations for our Monte Carlo calculation. So if you recall, last time and throughout the last few videos, we've built an expression for an expectation value of a given operator as a field integral over an auxiliary field sigma. This is our Hubbard-Satonovich field. There's a weight P of sigma, which if it's positive semi-definite, then we can associate with the probability. And then there's a quantity of interest X of sigma. So here, P of sigma is usually a determinant, especially if you're dealing with fermions, you're going to have some kind of determinant of a big matrix. This is going to be true in relativistic and non-relativistic theories. And then usually if you have gauge fields or other stuff, then you will have another factor here that depends only on sigma and does not take the form of a determinant. It will take a much simpler form. Here, Z is the partition function, the grand canonical partition function, which, as we saw in previous videos, is just a field integral over just the determinant of M of sigma. In this case, once again, if you have more complicated theories with extra weights here associated, extra exponentials and such associated with the field sigma, then Z is going to include those factors as well. And our job then, as I was saying last time, is that somebody needs to hand us our sigma field configurations, or our job is to generate them. This is going to be the topic of this video. But once you have them, then you can estimate this average by calculating this mean, this sum over all the samples of X of sigma and divide by the number of samples. And here, these are our samples. So how do we generate these samples? So the most vanilla way, or the simplest way to do it is very well known. It's called the Metropolis algorithm. And this is how it goes. You pick a starting configuration sigma 0, which could be completely random, or it could be totally flat, equal to a given fixed value for all your space-time points in sigma. And so you start with this configuration, you make a small change, and typically you will pick a few random points or a few places where to make your change, and that change is not going to be very large necessarily. And the next thing you do is you calculate this quantity little p here, this quantity p, which is the ratio of the probability associated with sigma 0 and the probability associated with sigma 0 plus that change. So we call this proposing a field change, and there's going to be a probability associated with it, and this may be larger or smaller than this p of sigma 0, the probability of the sigma 0 that you started with. And I'm calling this already a probability because I'm assuming that it's going to be a positive semi-definite quantity. And notice that here we don't need to calculate the partition function. This will factor out. That's one of the great things about this algorithm. You really don't need Z. Otherwise, we would be in a circular position, and we would need to calculate this in order to calculate something else. And both of these quantities are equally hard to estimate. And so we need to then go ahead and not worry about this with the Z is. We just need to go ahead and calculate this ratio, which amounts to calculating a ratio of determinants in this case. So once you have this ratio of probabilities, then you can decide if you accept this change in sigma 0 or not. And so if this quantity little p is greater or equal to 1, then you keep that sigma 1. You keep sigma 0 plus delta sigma, and you call that sigma 1. And so that's in the case that this probability p of the configuration with the change is larger than the probability of the place where you started. So if you're going to a place of larger probability, then you keep that configuration. If not, then you accept that change with probability p. And what that means, if you think about it, is that, well, if this p is less than 1, it's going to be somewhere between 0 and 1 here. And what you can do is you can throw a random number, and if it falls between 0 and p, then you accept that configuration. And if it's greater than p, if it lies over here, then you reject it, and your sigma 1 is equal to sigma 0. And so in this way, what you do is you generate a chain of configurations, sigma 0, sigma 1, sigma 2, sigma 3. If the change is rejected, then the sigma 1 happens to be equal to sigma 0. Otherwise, it will be different. And then you propose a new change, and you generate a sigma 2, which again, if the change is rejected, then it will be equal to sigma 1. Otherwise, the change is accepted, and you continue down this chain. So this process generates what's called a Markov chain. This is going to be our Markov chain. And if we wait long enough and sample snapshots along the way every so often, then allowing enough time in between the samples, then the resulting set sigma of k will be distributed according to p of sigma. And by enough time in between samples, what we mean is that we have to lose memory of where we started first of all, and we have to lose memory in between snapshots. And so we call that process decorrelation. And so first of all, you have to wait for the system to equilibrate to begin with, and that we call that thermalization. And so you have to wait a little bit for thermalization, and after that, once you start taking snapshots, you have to wait for decorrelation between samples. And you have to come up with a measure for that decorrelation. So what constitutes proper decorrelation between two samples? You can calculate the correlation between, for example, calculating the energy for one of the samples, and then you can recalculate the energy at a later point. And if those two energies are properly decorrelated according to some measure, usually we calculate the autocorrelation between samples, then you can take that other snapshot, and you proceed in this way, and every so often you take snapshots. Both of these quantities, both of these processes, thermalization and decorrelation, can be especially slow close to phase transitions. That's what's called critical slowing down, and that's something to watch out for. But we have a much bigger problem than this. All this is, of course, assuming that everything works and that we can perform these steps that we've figured out how to calculate determinants, how to calculate ratios of determinants, how to deal with random numbers. We have all this chain and so on. But there's a much bigger problem in the field than doing all that and doing that efficiently. And the problem is called the sign problem. And this appears when P of sigma, our so-called probability, our weight, does not have a definite sign. So then it's not well defined as a probability, and we have to do something else. And then we run into trouble, and you can find all sorts of articles on how to deal with the sign problem, on how to solve the sign problem in certain classes of theories. And I actually myself, with my students and colleagues, have written a review article on the sign problem, which you can find on the physics reports over the last few years. A natural question to ask is, well, if P of sigma doesn't have a definite sign, could we use the magnitude of P of sigma? And let me show you what happens when you try to use the magnitude of P of sigma. So first of all, suppose this is a quantity we're interested in, the expectation value of x, and so this is our probability now, or supposed probability, our weight, now written explicitly as the determinant divided by the partition function. And now what I'm going to do is I'm going to write this determinant as the magnitude times a phase. Okay, so in principle, this determinant could be a complex number. It could also be a real number with a not definite sign, but let's assume more generally that it could be a complex number for whatever reason, which actually happens in real applications such as finite density QCD and other interesting phenomena, other interesting systems in condensed matter. So you have a magnitude, you have a phase, and I'm going to write the partition function in the same way as the field integral over the magnitude of the determinant times the phase associated with that determinant. Now, why am I doing it this way? You will see. If I multiply and divide by the field integral over just the magnitude, which is what I intend to use as a weight, then I seem to have a proper now normalization for something where I'm going to average using this as a weight, this magnitude as a weight, and I have the integral over the magnitude here, and then I have to deal with this other crossed term over here. Now I have, if you look carefully, I have in the denominator then the average over x of sigma times the phase, where the average is taken with using the magnitude of the probability. And then in the bottom, I am basically dividing by the expectation value properly normalized of the phase of e to the I phi, where the average now, once again, is taken according to this magnitude, which is what we wanted, is what we're asking. Can we use P of sigma? The issue with this is that typically both the numerator and denominator here are going to go to zero. And they're going to go to zero exponentially with the volume of your space-time. And so as you try to go to lower temperatures and larger volumes to account for those systematic effects, or perhaps because you want to go to low temperatures because that's where the interesting stuff happens, phase transitions and quantum phase transitions and such, then both of these quantities are going to go to zero exponentially. And so you're going to have what's called a signal-to-noise problem. So both of these quantities, numerator and denominator, are going to go to zero. They're going to go to zero very quickly. But you want to determine this ratio. You want to determine what's left, that little bit of a contribution that's left from taking that ratio. And that's very hard to resolve numerically. And that's why we say you have a signal-to-noise problem. So in principle, you would need an astronomical amount of statistics in order to resolve that problem. And that's then another manifestation of the sign problem. As I was saying, this problem is everywhere. It's in condensed matter. It's a finite density, finite chemical potential QCD, in quantum chemistry, and in a number of other areas. And there's lots of literature and attempts to solve this problem. And that's about it. That's all I wanted to communicate with you. As I was saying, the main algorithm used for generating samples is the Metropolis algorithm. It's no different in a way as trying to do a very complicated Ising model calculation. And if you haven't done an Ising model calculation, then maybe I'll do a video about that in a future episode. And but there's a much bigger problem, which is the sign problem, which is in a way a motivation for going towards quantum computing. And I'll leave it here. I hope you enjoyed this video. I hope you found it useful and instructive. And if you did, please consider liking and subscribing. And as always, if you're looking for a tutor in physics or math in English or in Spanish, maybe I can help you. You can contact me at shorttext331@gmail.com, or you can leave a message in the comment section below and I'll get back to you. I'll see you next time.